Good evening, Cleethorpes. This is Astrophotography. As you can see from the subtitle, I'm talking about photographing the night sky, ideally without ridiculously expensive equipment. Because, as some of you no doubt know, astrophotography can get very expensive very quickly. So, with apologies for those of you who are already expert astrophotographers, I guess in this talk there will probably be nothing that you don't already know. So, what do you need to get into astrophotography? Well, in principle, you can start with next to nothing, just a camera and a tripod. If you wish, you can graduate to astrophotography using telescopes, in which case you'll need to have the telescope on a driven mount. An alternative is to use a camera and a star tracker, and I'll tell you in due course what I mean by star trackers. And I'll be showing you some of my images. Well, that's basically why I'm giving you this talk, so I can show you some of the images I've taken. And I'll finish with just a few comments about taking photographs of the night sky from the darkest skies that I know of, which are in the middle of Africa. So, starting with just a camera and a tripod, what can you do? Well, this is effectively where I started many years ago. This is probably, I don't know, about a quarter of a century ago. Back in the days when I didn't have a digital camera, I just had film. But I tried just pointing it at the sky. I was on holiday. I went to visit Egypt and see the pyramids. Whilst I was in the neighbourhood, out in the desert, I decided to point the camera at the sky and see what I could get. So this was something like a 5-minute exposure. Even though the data isn't recorded on film in the way it is for digital images, I can figure that this was a 5-minute exposure just by seeing how much the sky had rotated. There's Polaris right in the middle of the field there, hardly having moved in a 5-minute exposure. Polaris not very high in the sky because this was not taken from England, this was taken from Jordan, where at a much lower latitude, and hence Polaris is not high in the sky. So this was a wide-angle lens, 5-minute exposure. Where I know the details, I'll write them at the bottom of the screen there, so you know which camera and what exposures I've been using. Of course, you're not limited to just taking a few minutes exposure, especially now that we have digital photography. We can take either a very long exposure, or because we have the option with digital photography, we can take a whole series of short exposures and add them together in the computer. So this looks a little bit like a daylight picture in the foreground. It's a blue sky and apparently a well-lit foreground because it was taken on the night of a full moon. So this is where we take our students to Tenerife. Sometimes we get a full moon. We don't always get the new moon skies that we would like. So on this particular night, I took this 6-hour exposure from a series, you can see at the bottom there, a series of 360 1-minute exposures, and then added them all together. One advantage of doing it this way, apart from the fact that it's very easy to remove any images that were either bad because of a passing aircraft or satellite or other things, it also means that if you wish, you don't have to add them all together to make a star trail. If you wish, you can add them together to make a movie. In other words, you're adding them together sequentially, and you can see that to start with, Polaris looks like it's hardly moved at all, but if you watch it over the period of hours, you realise that Polaris does actually move in a small arc itself. It's a little less than 1 degree from the pole, so it does actually move in a small circle or arc of a circle. And so by taking a series of images like this, you can add the images together to make either star trails or to make a movie. The software that allows you to do this is free software that's available for Macs and PCs, and I guess Linux as well. So you don't have to worry about expensive software that will allow you to do this. So if you've got a camera that will take an exposure of 30 seconds or 1 minute, then you can take images like this. Of course, sometimes you have to be in the right place at the right time to get images, such as, for instance, a total eclipse of the sun. We had a partial eclipse fairly recently, but a total eclipse is rather rarer in the sense that on any particular place on Earth, you're unlikely to get a solar eclipse more often than once or twice a century or so. So this, again, didn't need any specialist equipment. This is just a camera on a tripod pointed at the sun, and this particular image was taken effectively mid-eclipse. A few different exposures to try and catch as much detail as possible within the solar corona. And also right place, right time. If you want to catch the northern lights at their best, then ideally you need to go to polar regions, somewhere around the Arctic Circle or Antarctic Circle. In this particular case, I went to Iceland with some friends. And again, pre-digital, this is taking images of the aurora. The exposures I'm not too sure about, but this was definitely a wide angle lens. You can see these beautiful curtains of light that rain down because of charged particles from the sun illuminating the gas molecules in the atmosphere. You get these shimmering curtains of light, and it was a wonderful experience to watch these curtains waving almost like curtains in the breeze over a period of hours. And perhaps you can see in the background there, in the middle of the image, there's the Pleiades, and over on the left, Orion is just peeking out from behind the side of the image there. Of course, it is possible to see the aurora from England when the sun is very active, as it is now. You tend to get a little bit of the reds and greens. You don't tend to see the structure of the curtains and the arcs and the rays in the same way you do in polar regions, but at least it is possible to catch the aurora in the UK when the sun is very active. In this particular case, this is just an iPhone picture from my bedroom window just before I went to bed. Now, if we think about what you can do beyond simply, I've got a camera, I can put it on a tripod, it is of course possible to take images through telescopes, and this is where it starts to get more expensive. No, you don't have to have that particular telescope. That would be great if you had a telescope like that. Of course, the Hubble Space Telescope is coming towards the end of its life. It's been up there since 1990, so it's now a venerable 35 years old, and it hasn't got many years left in it. So just watch on eBay just in case it ever pops up on there. If you've got a few billion to spare, perhaps you could afford to buy it, and then you'll be able to get wonderful images as long as it's still operational for a little while, such as, for instance, M51 Galaxy and the Pillars of Creation in the Eagle Nebula on the right-hand side. A couple of iconic images from Hubble. If you haven't got a few $1 billion to spare, well, 100 million will get you this. A 747 with an infrared telescope in the back. This is SOFIA, the Stratospheric Observatory for Infrared Astronomy. Recently decommissioned, so again, this may be appearing on eBay before too long if you fancy buying a 747 for yourself. The idea here is you get above as much of the atmosphere as possible, more so than you could simply by putting a telescope on top of a mountain, which of course is a cheaper way of doing it. If you only have a few million to spare, then you can buy yourself a telescope like the Liverpool telescope, for instance, sitting on La Palma, the world's largest robotic telescope. So you don't have to go out to La Palma to use it. It can be effectively entirely used by setting up a sequence of observations that you want, and then the telescope decides in which sequence it will take those images during the night. And it will produce, again, nice images of the Eagle Nebula or M51. Not as good as Hubble, perhaps, but then it's 1,000 times cheaper, so that's fair enough. If you've only got a few £100 or a few £1,000 to spare, up to, I don't know what the limit would be for amateurs, so I've put an arbitrary range of £250 to £25,000 is the sort of range that you might think about buying a telescope as an amateur purchase. And of course that can be anything from a relatively small refractor or Dobsonian for a few £100 up to almost professional level telescopes which are now available to amateurs for perhaps a 5-figure sum. A lot of amateurs relish the idea of buying themselves a telescope, such as, for instance, unfortunately no longer available, but something like a Meade Schmidt Cassegrain like this one. And they enjoy the idea of buying a telescope and then throwing as much tech at it as possible and turning it into a complete spaghetti machine and putting on as many different things with as many different cables as possible. It seems like a competition. He who has the most cables wins. Now, in some cases, that's a sort of necessary way of doing astrophotography. You do need a certain amount of technology to make sure everything works as it should. I'm not a technophobe, but I don't like the idea of having as much technology as possible. I like to treat things as basically as possible. But ultimately, if you want to do astrophotography on a telescope, it does start to get very technical, and it does start to get rather serious and expensive. People would argue, astrophotographers in particular would argue, spend less time thinking about the telescope and more time thinking about the mount. It's the precision with which the mount can move the telescope that determines how you can get the best astrophotographs. Especially if you've got a big heavy telescope, you really need a big solid mount to make sure that you can move the telescope accurately and track the object and keep the astrophotography, the astrophotographic object that you're interested in, as close to the center as possible and get the best possible images. Now, going for a nice sturdy mount is certainly a good idea, but people differ as to whether or not a mount such as that one indicated is worth $10,000 or £10,000. Whether it's worth it or not depends on how serious you are with your astrophotography. Some say you don't need that, others say it's a damn good investment. Spending many, many thousands on a mount will pay for itself in the long run if you are definitely interested in astrophotography rather than simply looking through a telescope and enjoying the view. For those of you, if you are thinking of buying a telescope, well, don't jump into it until you've been given good advice, probably from colleagues in your own Astro Society. And I've produced a short talk, which is a rough guide to buying a telescope for anybody that's starting out in that arena. But that's not what I'm talking about this evening. Where would you put a telescope if you had one? Well, if you've got a back garden the size of California, well, you would put it there. There's the Hale telescope, the largest telescope in the world when I was born, sitting there in Palomar, on top of Palomar Mountain. I went to visit it back in 1982 when I was a student. Gosh, that seems a long time ago now. When I visited that telescope, I thought, wow, this is amazing. This is the biggest telescope in the world. That's the biggest dome I've ever seen. When I grow up, when I buy myself a house, I'm going to have a back garden big enough to have an observatory like that. Well, that's what I said in 1982. Actually, what happens is, well, I had to downscale my aspirations a little bit. So in 1998, I bought myself a shed and converted it into an observatory. So the tarpaulin at the top comes off and then panels lift off to expose the sky. So back in the late 1990s, that's what my observatory looked like. You can tell this is a very old picture for a number of different reasons. One is the observatory is clean and there's no spiders in there, so that must have been very early on in its life. And you can tell from the age of the Meade LX telescope, and more importantly, you can tell from the laptop sitting behind it. The laptop is an absolute brick compared to the very thin laptops that we have these days. So yes, this picture is probably 25 years old or so. And of course, you can never underestimate the amount of joy you get simply from looking at our closest celestial neighbour, the moon. Simply watching the changing shadows of craters or mountains or rills, either from night to night or even from hour to hour as the sun angle slowly changes, can be quite fascinating. And yes, you can get some wonderful images of the moon, taking images through a large telescope. This is an image I took with a Nikon DSLR that I put on the back of a Celestron, and with a single snapshot, a single picture of 1/500th of a second, you can capture some wonderful detail. It might not come across too well in this particular image, so let me just show you separately the top half. There's the Mare Imbrium with Plato at the top and the wonderful Sinus Iridum on the left hand side, just catching the sunrise there, and the Apennines at the bottom. If I show you the bottom half of that image, it includes Copernicus. So again, in this single 1/500th of a second snap from the back end of a Celestron, you can get wonderful detail, and you can see similar levels of detail by eyeballing the moon with a large telescope. Truly wonderful views. And of course, if you've got the money and if you've got a large telescope, you can do wonderful astrophotography. Here's just a few examples of a picture, again with my Nikon DSLR bolted onto the back of a celestron. There's the Pillars of Creation. There's the Helix Nebula, low down from England, a little higher as observed from other latitudes. So this is in the constellation of Aquarius, effectively a planetary nebula looking very similar to what ultimately the fate of our sun has in store. That tiny dot in the middle there is the remnant, the white dwarf that's left after the rest of the atmosphere has been sloughed off. And the third image there, the Trifid Nebula. Again, one of my favourite targets simply because it's got such beautiful colours, the pink and the blue. I'm a great believer in taking natural colours where it's possible to do so. So all of these images, no false colour involved. And in this particular case, no filters. These are just literally Nikon bolted on the back, take a few images, and in this case, stack them together. A few short exposures added together. Now, a celestron, a 14-inch celestron, is certainly not the cheapest of telescopes. It's something that a university can afford, but it's rather tricky for individuals to afford. The same is true of solar telescopes. Now, when you're taking pictures of the sun, you really can't do it on the cheap. So when I'm talking about ridiculously expensive equipment, you really don't have a lot of choice with solar telescopes. You can certainly project the sun and you can get images of the disk of the sun and you can see sunspots and you can see those sunspots changing from day to day. But to get the sort of detail that I'm showing here, especially with the interesting detail around the sunspots and also the prominences at the edge of the sun, then really you need a solar telescope that works in either H-alpha or possibly the calcium line. This particular image was taken with a Lunt LS60, so this is not a particularly large telescope with an objective of only 60 millimeters, but unfortunately, because it's a solar telescope, it is significantly more expensive than a similar sized telescope for night work. A 60 millimeter refractor for use at night might only cost you hundreds of pounds, but a 60 millimeter solar telescope will cost you thousands of pounds. It's an order of magnitude jump in order to get images like this. But as I say, if you want an H-alpha telescope, it's very difficult to get one that's only £100, for instance. But there are alternatives to spending lots of money on big, expensive telescopes, and that's really what I'm getting at this evening. You can use a camera and a star tracker. So let's just remind you, again, apologies for those people who know all of this, but just a reminder of the background of how imaging works. Basically, film or CCDs, the charge coupled devices inside digital cameras, are effectively monochromatic, and so they basically collect all light of all colours. And if you want to take a monochromatic piece of film or a monochromatic CCD chip in a digital camera, you then have the option of putting coloured filters and taking 3 separate images in red, green and blue light and then combining them together. Of course, we've had colour film available for quite some time, and that's a very clever development where the filters were actually effectively embedded in the colour film emulsion itself. So light went through one filter into an emulsion, then through another filter into an emulsion, then through another filter. It's not actually red, green and blue because of the way they interact with each other, but by clever combination of filters and emulsion, it was possible to make colour film. With digital cameras, given that all CCD chips are intrinsically sensitive across all colours, the filters have to be placed in front of the individual pixels of the CCD camera themselves. And one conventional way of doing it, there's actually multiple ways of doing it, but a common way of doing it, if we zoom into the surface, is a so-called Bayer grid, whereby different pixels are filtered with red, green or blue, and you see that actually the pattern is twice as many green as there are red and blue. Simply that makes it easy to put 3 different colours into a 2x2 grid of squares and then repeat that pattern across the whole chip. So if you take a picture with a camera with a chip like this, and effectively all colour cameras have this sort of idea, what you end up with is the camera ends up with a red image, a green image and a blue image where clearly there are some pixels missing because each pixel only picks up one colour. But then the computer that's inside the camera, whether it be your digital SLR or mirrorless camera or your Astro camera, the computer effectively combines them together into a colour image by combining the red and the green and the blue together. Now, I'm not going to talk about all the different astronomical cameras that are available. I've tried to be as fair as possible by not necessarily picking out a particular manufacturer, but just picking out a few different examples. For instance, Bresser make a camera which is virtually a replacement for an eyepiece. So a relatively modest 2 megapixel colour camera, and it's only a couple of £100 or so. You can buy monochromatic or you can buy colour cameras with the Bayer grid that I've just described, and once you start getting high-end, large chip, large numbers of megapixels, it can start getting a little bit expensive. What is perhaps surprising when you first look into this is the fact that colour cameras and mono cameras of similar number of pixels and similar chip size are actually very similar in price. You might initially assume that surely the cost of adding the filters, a red filter on this pixel, a green filter on this pixel, etc., across the entire chip, that might add something to the cost of making the cameras. Actually, it is virtually no additional cost. It's a very easy thing to do when the camera is being made. The last stage of adding the filters is a very simple thing, and as far as most manufacturers are concerned, they don't differentiate between the two. Many manufacturers will make colour and mono versions of the same camera and often sell them at essentially the same price. But if you did want to buy yourself a mono camera, rather than sacrifice the resolution of having one pixel that's red, one pixel that's green, one pixel that's blue, etc., if you want to capture across every pixel in the image and filter externally to the camera, then you need what's on the right hand side, ideally a computer controlled filter wheel that will spin and produce the right filter for your set of images. That could be red, green and blue, or it might be narrowband filters that let through only the light of hydrogen or only the light of oxygen, for instance. But you can see that that adds expense. A filter wheel might be a few £100, and depending on the sort of filters that you want, you might be spending hundreds of pounds on the various filters in the filter set. So that's what I mean by not only telescopes and mounts, but astronomical cameras can start to get very expensive very quickly. But the point I'm getting to in this particular talk is you don't have to buy astronomical cameras. You might already have a camera. For instance, I've got a Nikon SLR camera. Other brands are available, whether they be Sony or Canon or Panasonic or all the other types of cameras that are available. And it doesn't necessarily have to be a digital SLR camera, a single lens reflex. It could be a mirrorless camera, a bridge camera. The point is, a lot of people already own cameras. So, do you really need to go out and spend even more money on an astronomical camera when you've already got a camera that you might be using for other purposes? And that's the angle that I came from. I've got nothing against the idea of spending money on telescopes or spending money on astronomical cameras. My point is, you don't need to. So what can you do if you've already got a camera? Well, all you need to do is to take out the rotation of the Earth. That's the only thing that's stopping you taking long exposure images of the night sky, assuming you don't want star trails, assuming you want stars to be pinpoints of light, not star trails. Then you need something to effectively derotate the Earth. And that is what a star tracker is. You don't have to buy one. You can buy one if you like. They cost at least £100 if you want to go and buy a commercial one. But you can build one for yourself. That's where I came from years and years ago. I thought, why should I buy a star tracker when I can just build one? So I got a load of aluminium from B&Q, a couple of AA batteries, a potentiometer, and a couple of door hinges. And then I built myself this particular star tracker. It costs about £25 or something if you want to build one for yourself. If anybody wants to give that a go, I will gladly pass on the instructions for how to build a star tracker for yourself for less than 50 quid, 20 quid if you already have the bits and pieces lying around. I'll gladly pass on the instructions as to how you can do that. If you don't want to build one for yourself, you can buy commercial star trackers. 20 or 30 years ago, there were very few on the market. These days, there are loads of them on the market. I happened to choose many years ago to try out this Ioptron sky tracker. That I'm not saying that's the best tracker in the world. All I'm saying is that that's the one I happened to choose 10 or more years ago, and I've been using it and it's great. But there are plenty of others made by other companies. What's inside a star tracker? Well, it's really just a motor in a box. It's very fancy to call it a star tracker, but effectively it's just a motor in a box. There's a few AA batteries there feeding a little bit of electronics, which makes sure that this motor turns at the right speed through a gearbox, driving this worm, which turns this wheel at the right speed. Remember, we want to derotate the Earth, and one sidereal day is 23 hours 56 minutes. So most of this internal circuitry and gearbox is simply designed to make sure that the worm turns at just the right speed, such that this disc turns at the rate of one revolution in 23 hours 56 minutes. And if your camera is bolted rigidly onto that and you line it up with the pole of the Earth, then you will have yourself a star tracker. So this is just a few pictures I've pulled off the internet. This is how other people have set them up. You can see that a number of people simply choose to put their camera on a ball and socket joint such that when the tracker is set up and the polar scope that you can see on the right hand side here allows you to make sure that you're pointing at Polaris, or at least pointing at the pole with Polaris slightly offset. Then the camera is put onto this disc, which turns at one revolution in 23 hours 56 minutes. And with a ball and socket joint, you can simply choose to point your camera in any direction you like. And you can choose to use a wide angle lens on your camera, or you can choose to use a telephoto lens on your camera. You have a choice. The only restriction is you can't put more than about 3 or 4 kilograms or so, but most cameras these days with a modest size telephoto lens will come in well under budget as far as the weight is concerned. I choose to use a Nikon. Again, other cameras are available, and even with a large telephoto lens, a little tracker like this can easily handle the weight. And rather than a ball and socket joint, I prefer a little sort of Altaz mount that allows me to easily change the position of the camera while it's sitting on the tracker. Now, in terms of the choice of camera and lens, one of my hobbies is wildlife photography, and I often use a Nikon. At the moment I'm using a Nikon D7500 SLR camera, and my lens of choice for taking pictures of lions, such as this picture of the lion on the left hand side, my lens of choice is a 300mm f4 lens. There it is there. You can see it's not a particularly large lens, it's a little bit larger than the palm of your hand. It's relatively small, relatively light. It's a lot shorter than 300mm because telephoto lenses are not the length of the focal length. The focal length might be 300, but the lens itself is only about 150mm from front element to rear element. So it's small, compact, lightweight, fantastic if I'm going on a safari and want to take a picture of lions. Gives me really nice, sharp images like the one on the left-hand side. But the question is, does a camera and lens combination that is designed to take pictures during the day, ideally on a sunny day, so a picture like that on the left hand side taken at sunset with a lion illuminated by the setting sun, just because it can take nice images during sunset, does it necessarily mean that that same combo can take pictures at night? Or do you really need an astro camera? You can see where I'm going with this. So I'm going to show you some of the images that I've taken with my Nikon on a star tracker, and I hope to convince you that you can take some nice images even without shelling out enormous amounts of money. If you've already got a camera, then with a relatively modest star tracker, you can take some nice images. And that's what I'm showing you here. There's a little montage of some of the images I've taken with the tracker. You can take pictures of the Milky Way, you can take pictures of nebulae, you can take pictures of supernova remnants, you can take pictures of galaxies. I'm not decrying the use of telescopes. Obviously, astrophotography using a telescope can be enormously rewarding, and I'm sure that some of you have already tried this and have produced some wonderful images of very distant objects. But I would argue to get the most out of astrophotography using a telescope will take quite a bit of time, quite a bit of effort, and quite a bit of cash. And my argument is you can't necessarily get rid of a little bit of effort and a little bit of time, but you can definitely get rid of the need for an awful lot of cash. So let's have a reminder of how things work. For those of you who've never taken a picture of the night sky before, bear in mind that when you take a picture of an object, here the North American Nebula, what you see on the back of the camera will probably look nothing like the finished article. What you see on the back of a camera might look like the left-hand side. There's a raw image. This was taken from an environment in England where there was plenty of light pollution around, and we can see that we can barely see the nebula because of the glow of the sky produced from local streetlights. But just because the raw images look a bit rubbish, that doesn't mean that you can't do something with them. Software, some cases free software, in some cases you might want to pay some dollars or pounds or euros for software that you use. Software will allow you to process those images, and you can see from the right hand side, with a little bit of tweaking, you can get rid of that horrible glow from light pollution, as long as it's not too bad, and you can bring out the detail in the stars and the detail in the nebula, in this case the North American Nebula. So it won't deal with the worst light pollution in the middle of a city, but moderate light pollution from suburban areas can be mitigated by the use of software to process your images and get rid of horrible color casts and bring out the sort of detail that you're trying to get in your images. Here's an image of the Rosette Nebula taken a few years ago. And again, this was a 300mm lens, but bear in mind you don't have to use a telephoto lens. This is a picture of the nebula surrounding Eta Carinae, and notice from the text at the bottom there, this is not taken with a 300mm telephoto lens. This is taken with an 85mm lens. Given that a standard lens on a camera might be of order 40mm or so, this is an effective magnification of ×2. We're not talking about huge magnifications. The Carinae Nebula is a huge nebula in the sky. It is much bigger than, for instance, the full moon. And so the idea that astrophotography will only work if you've got long focal lengths and high magnifications, that's true if you've got a really small target. But there are plenty of targets in the sky which respond to relatively modest focal lengths. Here, only 85mm, and in this particular case a 15-minute exposure taken as 15 1-minute exposures and then added together. This is the only image I'm showing this evening which was taken with a filter. Every other image I'm showing is completely unfiltered. So this was actually taken with the tri-band filter from a relatively light polluted area. I've tried photographing this object from a very dark sky and got some nice images. I thought I would try photographing the Veil Nebula from a light polluted sky, but using a tri-band filter. A tri-band filter lets through 3 particular wavelengths, notably 2 wavelengths from hydrogen. They come out in the red, one of the hydrogen comes out in the blue, along with oxygen, which comes out in the blue. So most of what we're looking at here, red is hydrogen, blue is oxygen. And essentially all other wavelengths, other than the narrow region around the hydrogen wavelength and around the oxygen wavelength, most other wavelengths have been blocked by the filter, which is why the light pollution doesn't have too much of an effect on an image like this. So again, this is a 300mm lens because that framed the Veil Nebula quite nicely, and this was a total of 1 hour's exposure. The tri-band filter I simply placed in front of the telephoto lens. The tri-band filter was designed to be used on eyepieces of telescopes or in astro cameras, but that doesn't mean you can't use it on any old lens just by holding the filter in front of the lens. So it was nice to see that tri-band filters do cut out light pollution, so you don't have to find the darkest skies possible if you're interested in objects which emit mainly in the hydrogen and oxygen or other particular lines. Doesn't work so well if you're talking about a broadband source such as a galaxy which emits across all wavelengths of the visible spectrum, but if you're dealing with nebula which tend to emit at specific wavelengths, then filters such as dual band filters or tri-band filters can work very nicely. This is an image, we've come away from filters now, so this is a natural color image of the Rho Ophiuchi part of the Milky Way, just a little bit north of the center of the galaxy. I like this area for a number of reasons, but mainly because it has this beautiful contrast between blue nebulae and yellowy nebulae, as well as some large parts of dark nebula that are in the foreground. So we get this contrast between a reflection nebula here in the blue, an emission nebula here, and these dark nebula producing these strands of darkness coming in front there. This particular area is in the interface, the boundary between Scorpius and Ophiuchus. So there's Antares, the brightest star in Scorpius. There's the M4 globular star cluster. That's Rho Ophiuchi itself. And this whole area is called the Ophiuchi cloud complex or molecular cloud complex. I took this image quite some time ago with a 135mm lens. But it struck me, I wonder if I can get any more detail if I swap to a 300mm lens. So that's going to be a smaller field of view, but given that I've captured all of this area and with a bit to spare, I wondered if it was worth imaging with a 300mm lens. So I tried imaging that area in the red box there, and this was the result. This was the result of a little more than, what was it, a little more than 2 hours of integration, a whole load of 60-second exposures on a tracker. And I was very pleased to find that I could get a lot of interesting detail in the blue and the yellow, and even some of the dark nebula are starting to show some very interesting structures as well. Like any astrophotography, the longer the exposure, generally speaking, the more detail you can see. And if you're taking a whole series of short exposures, then you don't have to worry too much about the accuracy with which the tracker can track. You don't worry about guiding, for instance. It doesn't matter if it's not absolutely perfect, because the software will add all of the individual frames together, making sure that everything is perfectly aligned. So I was very pleased to see all the subtle detail in the Ophiuchi Nebula there. Thinking further afield, everybody, at some point or another, everybody takes a picture of the Andromeda Galaxy. I think it's probably the law. Everybody has a crack at this. It just works really well with the 300mm lens. You can see the Andromeda Galaxy fills the frame quite nicely. I think I might have cropped a little bit off the outer edge of the frame, but essentially the Andromeda Galaxy nicely fills the frame. This is a half-hour exposure, 30 lots of 60 seconds. And again, you can see some wonderful detail. We've rather overexposed the core there. I could have processed this a little differently to try and avoid overexposing the core, but we've got some nice detail in the outer spiral arms of the Andromeda Galaxy. I was interested to take images of more distant galaxies, I wonder how far you can push the idea of a camera on a tracker. This is only 2.5 million light years away. This is effectively next door in galactic terms. So I tried Markarian's chain. Markarian's chain is a chain of galaxies about 50 million light years away. And you can see a number of fuzzy blobs here. There's a few dozen that you can instantly pick out. When you look in detail, if you blow this up and zoom in, you can see about 40 to 50 galaxies. Again, 300mm lens because that framed the Markarian chain group quite nicely, and I took a whole series. I can't remember why I backed off to 20 seconds here, but I backed off and took a large number of 20-second exposures. It might have been a little bit windy this night, and perhaps there was a little bit of vibration of the mount, but it doesn't really matter. You don't really lose or gain as long as the total exposure, when you add all of the individual frames together, the total exposure is what matters, not how many you've got of how long each individual exposure is. So again, I was picking up some structure of spiral as well as elliptical galaxies for all of the members of the Markarian chain there in the group that you can see. But not being happy with 50 million light years, I thought, well, how far can you go? I thought about that rather idly until something forced me into thinking about, well, let's actually give it a go. The thing that forced me into giving it a crack was COVID. We had a lockdown in 2020. I wasn't allowed to go out and socialize with people, so I thought, okay, I'll stay home. July 2020. Generally speaking, very short nights. You don't have much darkness in the middle of summer in the UK. But I thought, okay, I'm at home, let's give it a go. So I tried this lockdown challenge. Can I image with my camera on a star tracker the most distant galaxy possible? What would that distance actually work out to be? So I looked up a paper of all of the quasars. Quasars are simply galaxies with very active nuclei, active galactic nuclei. Basically supermassive black holes that are producing a lot of energy and so are visible at enormous distances. I found that there was one high in the sky in July as seen from the UK. So I thought that's the best one to go with. There were others that were even more distant, but they would have been low in the sky and not easily visible. So in July, I put my camera on my tracker, as I indicated before, Nikon plus a telephoto lens on the tracker, and pointed it essentially towards the zenith. This star that you can see in the middle there is a 5th magnitude star in the constellation of Draco. It's nice and high in the sky in the middle of July. I took a number of exposures, you can see on the bottom there. I took over 200 exposures of 30 seconds each, and I took exposures essentially continuously over a slightly more than 2 hour period. I ran from the evening dusk to the morning dusk, which in the middle of summer is only about 2 hours or so. A few frames were thrown away because clouds came and went, and there were a few aircraft as well. But apart from that, I was left with over 200 useful frames of 30 seconds each, so a couple of hours exposure. And according to the coordinates of the quasar I was hoping to catch, the quasar should be in the middle of that square. Having it close to a 5th magnitude star was handy because I knew which way to point the camera, and I could check that I was pointing at that star, and I could also focus on that star as well to make sure I was definitely in focus. So I took the images. Next day I added them all together, and then I zoomed into that square hoping to find this quasar right in the middle. And although it doesn't look very spectacular, there it is. That tiny dot there is a quasar. Now I appreciate it doesn't look very spectacular, but most of the light from this quasar apparently has been focused into just 1 pixel of the image. This camera has got 20 million pixels, but only one of them has caught the quasar. If we blow it up, we can see that that central pixel is the quasar. Perhaps a little bit of light has bled out into the neighboring pixels. I've exaggerated the brightness here. There's a few stars in the background there, so you can see a few pixels are recording the light from this quasar. What is remarkable is not the fact that this picture is a fairly dull looking picture. What is amazing is the distance to this quasar. 25 billion light years. In other words, the light has been travelling to get to my camera for 12.4 billion years. bearing in mind the universe is only 13.8 billion years old, that means the light, to get this image, the light had to travel for 90% of the age of the universe in order to arrive on the chip and produce the image. Second most remarkable thing about this image is that the galaxy is receding from us at twice the speed of light. Because of the expansion of the universe, we can translate redshift, which was calculated by the people whose paper I looked up. They calculated the redshift, and from that we can get the distance and the recession velocity. Because if we know the distance and we know the Hubble constant, we can calculate how fast these galaxies are receding from us. This particular galaxy is receding from us at twice the speed of light. And even when the light left this galaxy, it was receding from us not quite at that speed, but at 1.7 times the speed of light. So it is absolutely amazing that it is possible to capture the light from an object that's moving away from us at superluminal speeds. So all of these things are amazing, but I still am boggled by the fact that you can do this with a camera designed to take pictures in daylight. It's supposed to take pictures of lions and zebras and dogs and family and other things. And yet it's possible to take a picture of an object on the other side of the observable universe, where the light has been traveling for most of the age of the universe in order to arrive and hit the sensor. I think it's truly amazing that cameras that aren't designed to do that can do that. Let me just finish with a few thoughts about going to Africa. I'm interested in photography, I'm interested in wildlife, I'm interested in astronomy. And all of these overlap to some extent, because if you're interested in wildlife, you can watch them with binoculars, or of course you can photograph wildlife, like the picture of the lion I showed earlier. If you're interested in astronomy, you can use the same pair of binoculars, and you can dabble with the idea of astrophotography. Wildlife and astronomy actually overlap. Not only can you use the same optical equipment, binoculars, but also if you go to very remote locations on safari, then you're also getting away from street lights, which means astronomy is fantastic. So all of these overlap if you go on safari. I'm not necessarily telling you that that's how you have to have your holidays, but for me, it's an ideal way of spending time. Basically, I can photograph and watch animals by day, and I can look at the skies and photograph the skies by night, and basically sleep when you get home. It's the best sort of holiday that I can imagine. If you're using a sky tracker, then often they will have some sort of a polar alignment, a polar scope, to make sure that the axis of the rotation of the star tracker is lined up with the pole. And there's a reticle inside, and what it looks like is shown by this app here. And the app tells you, given that the app on your phone knows where it is because of GPS and it knows the time, therefore it can tell you that when you're looking at the North Pole, if the North Pole is bang center in this reticle, then Polaris ought to be visible at this particular point. So all you have to do is look through the polar scope and jiggle it around until Polaris is in the place indicated by the dot, and that tells you that you are quite definitely lined up to the North Pole with an accuracy of a few arc minutes or so. That's very easy to do in the UK. I've done it many, many times. However, the North Celestial Pole, of course, is directly above the North Pole of the Earth. Not a problem if you're at latitude 52 degrees, because that means that the altitude above your northern horizon of Polaris is about 52 degrees. But if you go to Kenya or Tanzania or anywhere in East Africa, you are very close to the equator, which means Polaris is very close to the horizon and probably hidden behind an elephant or something like that. So actually, in practice, using a tracker in Kenya or Tanzania is actually rather tricky, because you can't see Polaris and you can't see the southern pole either, for the same reason. It's on the other horizon. So you can use a magnetic compass to tell you which way is north and you can check your latitude from GPS and figure out how high the North Celestial Pole or South Celestial Pole is above the horizon, but it involves a little bit of guesswork. So you can't line them up quite as well as you can from the UK, but it doesn't stop you taking nice images. Here's the Large Magellanic Cloud, for instance, something that you can't see from the UK, and I was quite keen to photograph from the equator. Notice again, this doesn't require a long telephoto lens, 85mm lens. This is effectively a ×2 magnification. The Large Magellanic Cloud is a very large object. And this is my attempt to give you an idea of what the Milky Way looks like. As seen from the UK, on a dark night, you might catch the Milky Way running across the sky. But the Milky Way, when you get away from streetlights, looks so much brighter, almost to the point where it starts to cast shadows. And with the naked eye, you can see all of this wonderful detail of the bright patches in the Milky Way and these dark nebula, like the Pipe Nebula and the strands reaching across to Rho Ophiuchi that I showed you earlier. All of this structure in the dark dust and the bright regions of the Milky Way are easily visible by eye when you get away from streetlights. And of course, as soon as you do some astrophotography, then you get the colour coming in as well, which you don't see with your eyes, simply because your eyes are not colour sensitive at low light levels. This particular image, you can probably tell from the black rectangles in the corners, is a little montage. It was taken with a wide-angle lens, a 35mm lens, and it was a few lots of 2 minutes. When you have wide-angle lenses, you can certainly take longer exposures because the tracking accuracy doesn't really matter when you've got wide angles. If you want to take telephoto images, then you have to ideally get your tracker lined up as accurately as possible. If we have a look at a little more detail, here's the image again. We have two interlopers in this image. There's the very bright Jupiter, and over on the left-hand side we have Saturn. And I have spent many a long hour looking at images like this and picking out all of the interesting nebulae and star clusters that are visible even in just a wide-angle view. And I can label these are just the Messier numbers. I haven't even attempted to show the NGC numbers because the entire image would just be covered with them. There are dozens of M numbers and literally hundreds, if not thousands, of NGC numbers buried in there. They seem to stop at that point as if nothing interesting happens if you go further south, but remember that's not because the Milky Way isn't interesting down there. It's simply because Messier observed most of his clusters from France and he couldn't see any further south than that as seen from Europe. So my point basically is star trackers are great. They are small, light, easily thrown into your luggage. If you're going to go on holiday somewhere interesting and you're going to go somewhere away from streetlights, why not throw in a little tracker? They are relatively small, they add very little to your luggage allowance. If you're taking a camera anyway, why not take a tracker, and then you can take the sorts of images that I've been showing you. The universe is out there for the sake of a small box that allows you to derotate the Earth. The universe is out there and you can photograph it for yourself for not exactly nothing, but I would argue close to nothing. Thank you for listening.